Aloha BIOCHEM. In this lecture, we are continuing in Chapter 1 and discussing scientific notation. Hello again. So we're moving along in the chapter, and in this video we cover section 1.6, scientific notation. You may have seen scientific notation used before. It's a way that helps people represent very large numbers or very small numbers. Numbers that would take a long time to write out and really be difficult to read otherwise. So it's helpful. It's supposed to be helpful. What a scientific notation number looks like is written in green right here. A times a power of 10, where A is a number between 1 and 10, and this is an integral power of 10. So 10 raised to some integer, where 10 to the b, where b is any integer. So it could be 10 cubed, 10 to the 5th power, 10 to the negative 2nd power. It could be any integer, positive or negative. So I hope you remember what powers of 10 are, but if you don't, that's okay. Powers of 10 look like the following. So 10 cubed would be 10 times 10 times 10, which is 1,000. 1 followed by 3 zeros. 10 squared would be 10 times 10, which is 100. 1 followed by 2 zeros. And then 10 to the 1 power would be 1 followed by 1 zero. 10 to the 0 power would simply be 1. It's not 0, it's 1. And then when you get to negative powers of 10, the numbers get to be smaller than 1. So 10 to the negative 1 would be 1 over 10, which is 0.1. 10 to the negative 2 would be 1 over 100, or 0.01. And 10 to the negative 3 would be 1 over 1,000, or 0.001. And hopefully you see the pattern. 10 to the 8th power would be 1 followed by 8 zeros. And so this can be helpful. So if you have, say, 10 to the 23rd power, we see that power of 10 quite a bit in biochemistry. And that would take quite a long time to write out. 1 followed by 23 zeros. And I don't think anybody would want to look at that number. It would be so long. So that's powers of 10. So a power of 10 is just part of scientific notation. You have to have a number between 1 and 10 multiplied by a power of 10 for it to be scientific notation. So let's look at a few examples. Here are 3 examples of measured values. So the first one is a distance. Suppose the distance is 2.9979 times 10 to the 8th meters. So you have a number between 1 and 10 multiplied by a power of 10. So that satisfies the criteria. This isn't scientific notation. A number between 1 and 10 times a power of 10. This, by the way, is the distance that light travels in 1 second. If you wanted to see what this number looks like in normal form, so if you get rid of the power of 10, if you just take these two and you plug it into your calculator, 2.9979 times 10 times 10 times 10, 8 times, that would do it. Your calculator would spit out this. So this is what it would look like in normal form without scientific notation. So this isn't too bad. You could write it either way. It would take about the same amount of time. But look at the next one. So suppose you're estimating the number of atoms of carbon in a pile of soot. So, it would be hard to count them precisely, but you could estimate it. 6 times 10 to the 23rd atoms is what you estimate. Imagine writing this one out. So 6 times 10 times 10 times 10, 23 times. you would end up with that many atoms. 6 followed by 23 zeros. So I would get lost counting them. But you can check it. I've checked this many times. It is correct. So you can try it, but I don't know. Is this like a million? It's hard to look at this number and see how many zeros. I don't know how many of the. If you were to just ask me to guess how many zeros, it looks like 18 zeros, but it's actually 23 zeros. So it's hard to, look at really large or really small numbers. So scientific notation can be helpful. The next one, 2.0 times 10 to the minus 6 grams of mercury. So now we're getting smaller than 1. So 2.0 times 10 to the minus 6. So now this is going to be a very small number of grams. So if you wanted to see what this one looks like in normal form, it would be 0.0000020 grams of mercury. So it's a very small amount of mercury. Now, you should be able to go back and forth between the number in normal form and in scientific notation. So if you have a number in normal form, you should be able to convert it to a number in scientific notation form and vice versa. So let's do the first one. Let's take this number which is in normal form and let's convert it to scientific notation form. The way you do it is you locate where the decimal point's supposed to be. It's not written here, but it's supposed to be there. So that's where it's supposed to be. And to get to scientific notation, we need to have a number between 1 and 10 multiplied by a power of 10. So the way you do it is you move the decimal point over right there to give you 2.9979. That would be a number between 1 and 10. You see, if you moved it anywhere else, it would not be a number between 1 and 10. If you moved it right here, it would be less than 1, 0.29979. If you moved it right there, it would be greater than 10. So you have to move it right here. And doing that, you're moving it 8 positions to the left. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and when you move the decimal point 8 positions to the left, to finish, you give it a power of 10 to the 8th. Okay. So to convert this to scientific notation, you move the decimal point 8 positions to the left. That gives you 2.9979, and then you give it times 10 to the 8th because you moved it to the left. Now, to go backwards, suppose you have this, it's in scientific notation, and you're asked to write it in normal form. Well, you just do it backwards. So you see that power 10 to the 8th. Okay, that means you take this part, and to get rid of that 10 to the 8th, you move the decimal point back 8 places to the right. So 1, 2, 3, 4, and then 5, 6, 7, 8, and that will give you this thing right here. All right, so you should be able to go in any direction. Now, let's do this one down here, the mass of mercury. So let's start with a scientific notation, and let's convert it to normal form. So 2.0 times 10 to the minus 6. Now this is a negative power of 10, so we're going to have to do it the other way. To get rid of a negative power of 10, instead of moving the decimal place that way, which would give us a very large mass of mercury, we have to move it the other way to give us a small mass of mercury, because this is a small number. So when you have 10 to the negative 6, you take your decimal point and you move it to the left 6 positions to get you this, 0.000002 grams of mercury. And to take this normal form and convert it to scientific notation, here's your decimal point, and then you have to get a number between 1 and 10, so that means you put it right there. That would give you 2.0, and moving that to the right, makes this number, bigger, 0.000002, to 2 would make it bigger, so you give it a smaller power of 10, 10 to the minus 6. So you move the 6 positions to the right, you get 10 to the minus 6. So practice that, taking numbers and converting them to scientific notation and back. So let's do a few more examples. Suppose you have some measurements that are not in scientific notation and you want to convert them to scientific notation. So 625 milligrams. Well, this is not in scientific notation. The decimal point is right there. So what we need to do is we need to move it right there. That would give us 6.25, which is a number between 1 and 10. And since we moved it to the left to get 6.25, we moved it 2 positions to the left, so it gets 10 squared. And now the next one. This is, a smaller than, a small volume, 0.0050 liters. So the decimal place is over there, and this time we have to move it to the right there. So to get 5.0, and we moved it 3 places to the right, and so since we moved it to the right this time, it gets a negative power of 10, 10 to the minus 3, because we moved it 3 positions to the right. By the way, if it were me, rather than writing the volume like this, I would rather write it like that, 0.0050 liters. I don't always write things in scientific notation, and other people don't either. You do it when it's useful. Okay, but it's good to do these exercises. In fact, if it were me, I would probably not write either of these. I would just say, well, 0.0050 liters, that's 5 milliliters. Okay, why am I using liters when I would rather use the milliliters unit? So 10 to the minus 3 liters, that's 1,000th of a liter, that's a milliliter. So you have 5 milliliters. Okay. The next one looks like it's in scientific notation, but it's not. So you have a number times a power of 10, but this is not a number between 1 and 10. This is 7,300 times 10 cubed microliters. 7,300 times 10 cubed microliters. So we have to fix this, and so let's convert. Let's change this, and the decimal point is right there. So we have to move it over here to get 7.3, and when we move it right there, we're moving it to the left again. Okay, remember when you move something to the left, that gives you a positive power of 10 that you add to it. So we're moving the decimal point 3 places to the left. So we're going to get 7.3, and then we get a 10 cubed to go with it. But we already have a 10 cubed. Okay, so we have 7.3 times 10 cubed times 10 cubed. So 10 cubed times 10 cubed equals 10 to the 6. So you combine those powers of 10 to get 10 to the 6. Remember, 10 cubed is just 10 times 10 times 10. So put that aside for the moment. So you have 7,300 and then times 10 cubed. But then 7,300 itself is 7.3 times 10 cubed. So you have 7.3 times 10 cubed and another 10 cubed. So that's 7.3 times 10 times 10 times 10 for the first 10 cubed, and then times 10 times 10 times 10 for the second 10 cubed. That's 10 times 10 times 10, 6 times. So that would be 10 to the 6. And then the units are microliters. But again, I probably would not want to even describe a volume like that, because I know that 10 to the 6 microliters, that's 1,000,000 microliters. I know that that's the same thing as a liter. I wouldn't say either of these. I would say 7.3 times 10 to the 6 microliters, that's the same thing as 7.3 liters. Okay, but again, these exercises are helpful in getting more comfortable in manipulating powers of 10. So one more example on taking a number that's not in scientific notation and converting it to scientific notation. So here we have 0.0020 times 10 to the minus 3 kilograms. So again, it's almost in scientific notation. We have the power of 10, but this is not a number between 1 and 10. So when we take the decimal point and we move it right there, which is where it's got to go to give us 2.0, we're moving it to the right this time, 3 positions. 1, 2, 3. Okay? 1, 2, 3. And so this right here by itself would be 2 times 10 to the minus 3, but we already have a 10 to the minus 3. So 10 to the minus 3 and 10 to the minus 3 equals 10 to the minus 6. Another way to think about these last two examples, okay, when you already have your power of 10, if you take that decimal point and you move this, you change this by moving the decimal point to the left, that bumps your power of 10 up. So you already have 10 cubed, and if you're moving this to the left by 3 positions, then you move this up by 3 positions to 10 to the 6. And the next one, you already have your power of 10, but this time you have to move the decimal point to the right. 1, 2, 3. So you're moving it to the right 3 positions, so you're going to, downgrade your power of 10. You're going to go down 3 positions, to minus 6. So that might be a better way to remember it. Okay, and by the way, 2 times 10 to the minus 6 kilograms is the same thing as 2 milligrams. It's 2 milligrams. Now, there's one more thing that makes scientific notation helpful. It's very easy to quickly count how many significant figures is in a scientific notation number. So let's go back up here to these first examples. When you look at a scientific notation number, you might say, how many sig figs is in there? Well, ignore the power of 10 part and just look at the number between 1 and 10. You always count every position. So 1, 2, 3, 4, 5 sig figs. This one has 1 sig fig because you ignore that, and then I only see 1 digit position over here, so that's 1 sig fig. Okay? It's easier to see that this is 1 sig fig versus looking at that. Okay, do I count the zeros? Do I not count the zeros? I don't count the zeros because I don't see the decimal point, and this is 1 sig fig. But when you look at the scientific notation part, it's easy to see how many sig figs. So here, the next one, ignoring the power of 10 part, you count every digit position over here. So this is a 2 sig fig number over here, but over there, you might, have a little trouble remembering how to assign sig figs. Well, you never count any of the zeros to the left, but you do count this 0 to the right because you see the decimal point. So this would be a 2 sig fig number, but that might be a little harder to do than just, looking at the scientific notation representation. So going down here, after we converted these to scientific notation, it's easy to see how many sig figs. This one has 3. This one has 2, 2, and 2. Okay, so one more, two more examples, and then we'll end the video. Suppose you have a number that's in scientific notation, say a distance, and you want to multiply it by another measured distance which is in scientific notation. So 3.0 times 10 squared centimeters multiplied by 5.0 times 10 cubed centimeters. This is not too difficult to do. Here, What's inside parentheses is you're multiplying things, 3 times 10 squared, and then you multiply what's inside this parentheses, 5 times 10 cubed. You're just multiplying and multiplying this by that, and so all you're doing is multiplication here. You don't really need the parentheses, so get rid of them. And then when you're just multiplying things, you can do it in any order. So go ahead and multiply the 3 and the 5 first, and then the 10 squared, and then the 10 cubed afterwards. And then don't forget to multiply the units at the end. So 3 times 5, that's going to be 15. And then 10 squared times 10 cubed, the rule for multiplying powers of 10 is you add the exponents. 10 squared times 10 cubed is going to be 10 to the 2 plus 3, or 10 to the 5th. And if that doesn't make sense, think about it like this. 10 squared is 10 times 10. And then multiplied by 10 cubed, that's another 10 times 10 times 10. So you're multiplying by 10 5 times. Okay, so that's 10 to the 5th. So, and then centimeters times centimeters would be centimeters squared. Now, you're almost there. You want to report the answer in scientific notation. So you got 15, and then you move the decimal point over to the left to get 1.5, and that bumps you up to 10 to the 6. So you got 1.5 times 10 to the 6 centimeters squared. And I know that this is a 2 sig fig answer because I have 2 sig fig distance times 2 sig fig distance. So the answer has got to be 2 sig figs if you apply your sig fig rules for multiplication and division. So 1.5 times 10 to the 6 centimeters squared. Now the last example in this video is we're going to divide two measurements that are written in scientific notation. So 8 times 10 cubed grams over 4 times 10 squared grams. Now here we can do the divisions in any order. So we can do 8 divided by 4, which would give us 2. And then gram divided by gram would cancel out. We'd have no units. But then what about 10 cubed divided by 10 squared? How do you divide powers of 10? Well, you would do 10 to the 3 minus 2. So it would be that, a little bit different rule. When you multiply powers of 10, you add the exponents. When you divide powers of 10, you subtract the exponents. So the 3 minus 2, which would be 10 to the 1 power, or simply 10. Another way to remember that is, upstairs you have 10 times 10 times 10, and then downstairs you have 10 times 10. So 2 of those upstairs would cancel the 2 downstairs, and so you'd be left with 1 upstairs. Or you have 1,000 divided by 100 would give you 10. That's another way to think about it. Now, 2.0 times 10 to the 1, that's simply 20. So you got 20 point would be the answer here. This is a 2 sig fig result because you had 2 sig fig mass divided by 2 sig fig mass. So you're going to get 2 sig fig as the result. So that's a little bit about scientific notation. We went through it in a pretty detailed way, so maybe more detail than what your textbook, how a textbook handles it. So I hope that helped, and I hope it made sense. In our next video, we're going to do some problem solving. So we're going to use all this apparatus that we've just learned about significant figures and scientific notation and units, and we're going to use that to attack some real problems that you might come across in science, in the medical profession. So stay tuned for that. Aloha.